Hello, in this video we're going to go over exam 3 from spring 2024, and this is on multivariable calculus course. So an object occupies this solid E bounded below by the paraboloid z equals x squared plus y squared. So we're going to first start drawing the shape that we are given. Z equals x squared plus y squared is a paraboloid. The vertex is at the origin and it is opening up. So something like this. And above by the plane z equals 2. So we have this plane right here. So this is our solid because it says it's bounded below by this and above by the plane. The mass density of this object at every point is the distance to the origin. First, set up a triple integral. So I'm going to write down the solution to 1a right here. In fact, the solution to 1a would have to include the diagram. So I'll just move that a little bit to the right and we'll start writing down the solution. Okay, so what is the density function? The density is the distance to the origin. So it's the square root of x squared plus y squared plus z squared. And then we want to find this one in Cartesian coordinates. So the total mass is going to be triple integral over E, this is the object E, of the density function, which is square root of x squared plus y squared plus z squared dv. And they said then turn this integral into an iterated integral in Cartesian coordinates. So in order to turn this one into an iterated integral, triple integral in Cartesian coordinates, we'll have to first find the projection onto the xy plane. So z equals root x squared plus y squared and z equals 2. So this gives us x squared plus y squared equals 4. So the projection onto the xy plane is a disk of radius 2 centered at the origin. So this is the projection onto the xy plane. So in this region is both a vertically simple region and a horizontally simple region. So we need to figure out what's the top of this region and what is the bottom of this region. The top of this region is y equals positive square root of 4 minus x squared. And the bottom of this region is negative of the same thing. So y equals negative root 4 minus x squared. So now we can write it down. So it would be triple integral integrand, which is root x squared plus y squared plus z squared dz dy dx, or we could do dx dy. I did it as a vertically simple region, so it would be dy dx. Bottom of the solid is x squared plus y squared. Top of the solid is 2, so that those are limits of z. Next we'll have to look at limits of y. Limits of y are bottom of R, this region R, and top of the region R. So negative root 4 minus x squared and positive root 4 minus x squared. And limits of x are left, which is negative 2, to right, which is 2. And they said do not evaluate the integral, so that is our answer. Next part of the problem is turn the triple integral, oh, and this is actually misspelled. Turn the triple integral in the previous part into an iterated triple integral in cylindrical coordinates and do not evaluate. So we have the diagram here. We'll have to just turn it into a triple integral in cylindrical coordinates, triple iterated integral. Okay, so we will do that. First, the integrand is going to be root r squared plus z squared. We'll have to change everything to r, z, and theta. dv is r dz dr d theta. Now, if we look at the limits of integration, they would be from the bottom of the solid, which is z equals x squared plus y squared, and that becomes r squared, to the top of the solid, which is z equals 2. And then r would have to come from the projection onto the xy plane, and the radius is 2, so 0 to 2 and 0 to 2 pi, because the projection has points in all different quadrants. So that would be our answer. And they also specified do not evaluate. So we just leave it like that. Next problem. Let E be the solid that lies above this cone. So let's graph the diagram again. Always we need to draw the diagram. So above this cone, let's do that. Sometimes they might use inside the cone or above the cone. So above this cone means, if you look at the cone like this, it means this region. All of this region is above the cone. It means z is greater than square root of 3x squared plus 3y squared. Inside the sphere, z equals x squared plus y squared plus z squared equals 3. So what is inside the sphere? We'll have to draw this sphere. So we will do so. We have this sphere, z equals x squared plus y squared plus z squared equals 3. So something like this. And of course, we have the same portion in other parts, but we don't need the other parts. So it's inside this sphere and outside this sphere of radius 1. So this one is root 3. The radius is root 3. And it's also outside this sphere of radius 1. So it's going to be something in between, the region in between them. So if we look at the intersection here, it would be this region right here. This is called E. Sketch a diagram and set up an iterated triple integral in spherical coordinates that is equal to this one. So if we look at a ray from the origin, the largest and smallest are on the spheres. So the largest of rho would be on the smaller sphere, which is, so r squared plus z squared equals 1 is x squared plus y squared plus z squared equals 1, which is rho equals 1. And the other one, x squared plus y squared plus z squared equals 3, is rho equals root 3. So these are the limits of rho. Limits of theta phi would be from 0 to the cone. So we'll have to turn the cone, which is z, which is rho cosine of phi, equals root 3 times r, which is rho sine of phi. So this gives us cotan of phi is equal to root 3, which means phi is pi over 6. So that's the largest value of phi. So now we are ready to set up the triple integral. So this is going to be, so we'll write it down. Let's write down the integrand. So what is x, y, z? So x, y, z, we'll have to turn that into spherical coordinates. So x is rho sine phi cosine of theta. Y is rho sine phi sine of theta. And z is rho cosine of phi. And dv is rho squared sine phi d rho d phi d theta. And then limits of integration. Rho goes from 1 to root 3, as we had the discussion earlier. Phi would go from 0 to pi over 6. And theta would go from 0 to 2 pi because we have points in all quadrants. So this would be our answer, and they said do not evaluate, so we're just going to leave it like that. Okay, so let's now move on to another problem. The next problem is evaluate this iterated integral. Well, we know that cosine of x squared dx cannot be integrated. So that cannot be evaluated. So because of that, we'll have to switch to dy dx. So we're going to write down, we're going to draw the region determined by this. So x is between y and root pi over 2. And y is between 0 and root pi over 2. So let's draw y equals x. So x goes from here to root pi over 2. So this is our region, which is a vertically simple and a horizontally simple region. So what we're going to do is we're going to take advantage of the fact that this region is also a vertically simple region. So the integral that they gave us, so the given double or iterated integral is double integral over this region of cosine of x squared. Now what we're going to do is we're going to switch the limits of integration and we're going to do dy dx this time. So we're going to do cosine of x squared dy dx. So what are the limits of integration? For y, it goes from the bottom of this region is 0, to the top. What is the top? Top is y equals x. And now we know that limits of uh, x are going to be from 0, which is here, to root pi over 2. So 0 to root pi over 2. Next, we're going to have to evaluate this one. So this would be integral from 0 to root pi over 2. Integral of cosine of x squared is y cosine of x squared. Y goes from 0 to y equals x dx. So 0 to root pi over 2. When we plug in x, we get x cosine of x squared. When we plug in 0, we just get 0. Now, this integral is just sine of x squared, but we need to divide by 2 because derivative of sine of x squared is cosine of x squared times 2x because of the chain rule. So I'll have to divide by 2 to adjust for that. And this goes from x equals 0 to x equals root pi over 2. So it is equal to sine of pi over 4. If I plug it in, I get pi over 4 divided by 2 minus sine of 0 divided by 2. And this is root 2 over 4. Okay, so next one. Consider the part of the surface given by x squared plus z squared equals 4 that lies between y equals 1 and y equals 4. So y equals 1 is right here, y equals 4 right here, and it's a cylinder uh, based on that axis, based on the y-axis. So we have something like this. So this is our surface. Draw a reasonable sketch of this surface and find a parametrization for this surface. So a parametrization that is reasonable is cylindrical, but because we have x squared plus z squared equals 4, we'll have to use a cylindrical adjusted, like in the xz plane, on the xz plane. In other words, the two variables would have to be theta and y. Because x squared plus z squared equals 1, we have to parameterize that circle on the xz plane by theta, and the radius is 2. So this would be 2 cosine of theta y, and then 2 sine of theta. And then what are the limits of theta? Well, theta goes from 0 to 2 pi because it's a full cylinder, and y goes between the limits that they gave us, so 1 to 4. Next one is find the equation of the plane tangent to the surface at that point. So we have to find the normal vector and we have the point, and then we can write down the equation of the plane. So let's first find Ry. If we look at this parameterization, Ry would be 0, 1, 0, and R theta would be minus 2 sine theta, 0 to cosine of theta. Next, we'll have to plug in the values for the point that they gave us. At this point 2, 2, 0, we'll have 2 cosine of theta, y 2 sine of theta is equal to 2, 2, 0. So what does that mean? It means cosine of theta is 1, y is 2, and sine of theta is 0. Now that means r y is going to be 0, 1, 0, and r theta would be 0, 0, 2. Then we're going to find the cross product of these two. So ry cross r theta would be, the first component would be 2 if we eliminate the first column. The second component and the third component would be 0. So this is the normal vector. So tangent plane is going to be 2 times x minus the point plus 0 times y minus the y value plus 0 times z minus z value equals 0. And that's just x equals 2. So that's the tangent plane to the surface at the given point. Okay, so the last thing we're going to do is a double integral, evaluating this double integral over this specific region that they gave us. Consider the region R in the xy plane given by that. Using an appropriate change of variables, evaluate this. So the easiest change of variable would be using some sort of an adjusted polar coordinates. So notice that this is not exactly polar coordinates because this one is not radius, because we don't have x squared plus y squared less than or equal to 1. So if you draw this region, this region is a inside an ellipse. So the intercepts are 1 and -1 on the x-axis and 1/2 and -1/2 on the y-axis. So it's this region. This is the region R. So what we need to do is to write down x as r cosine of theta and 2y as r sine of theta. R goes from 0 to 1 and theta goes from 0 to 2 pi. So now we can find the Jacobian with respect to r theta of xy with respect to r theta. So the Jacobian of this with respect to r and theta would be, so we take the partial of x with respect to r, that would be cosine of theta. Partial of x with respect to theta, that would be minus r sine of theta. Partial of y with respect to r, it would be sine of theta, but divided by 2. So 1/2 sine of theta. And finally, partial of y with respect to theta, which is r over 2 cosine of theta. So this would be r over 2 cosine squared of theta plus r over 2 sine squared of theta, which is r over 2. So this is the Jacobian. So integrating over r, we get, so we'll have to set the limits of integration. Limits of integration are coming from the r theta plane, which are r goes from 0 to 1 and theta goes from 0 to 2 pi. So this is our new region. So we could say 0 to 2 pi and 0 to 1, those are the limits of r. Now x is r cosine of theta and y is r over 2 sine of theta. So if we square them, we get these. Now we'll have to multiply by the Jacobian, which is r over 2 dr d theta. Now we can integrate. So the rest is going to be integration. So this is going to be integral from 0 to 1 r cubed over 2 cosine squared of theta plus r cubed over 8 sine squared of theta dr d theta. Once we integrate, the first integral is actually pretty simple. So that's integral from 0 to 2 pi. First integral is going to be r to the 4th over 8 cosine squared plus r to the 4th over 32 sine squared of theta from r equals 0 to r equals 1. So that is simple enough. But the integral with respect to theta is something you will have to remember from single variable calculus. Okay, so when we integrate sine squared and cosine squared, we'll have to use half angle formula. So this is integral from 0 to 2 pi, 1/8, 1 plus cosine of 2 theta over 2 plus 1 over 32, 1 minus cosine of 2 theta over 2 d theta. Okay, so let's do that. So this is going to be the first one, integral of, so let's just write it down one more step. So this would be 1 over 16 plus 1 over 16 cosine of 2 theta plus 1 over 64 minus 1 over 64 cosine of 2 theta. Now once we integrate, we get theta over 16 plus, what is integral of cosine of 2 theta? That would be sine of 2 theta divided by 2. And the integral of 1 over 64 is theta over 64. And then minus 1 over 64 sine of 2 theta divided by 2. And theta goes from 0 to 2 pi. When we plug in 2 pi, we get 2 pi over 16. Sine of 2 pi is 0. Sine of 2 times 2 pi is 0. We get 2 pi over 64. Sine of 2 times 2 pi is also 0. And then when we plug in 0, everything becomes 0. So this would be our answer to the problem. And that brings me to the end of this video. So I will see you in the next video.